Alrighty, so our last unit was kinematics. Kinematics is the study of blank objects move. How objects move, right? We talked about the position, the speed, the acceleration, and how they're getting from point A to point B. Okay? The dynamics is going to be the study of not how, but why objects move. And that means we're talking about pushes and pulls. And a blank is a push or pull. What was that word? You learned that in middle school, hopefully. Force. Is there push or pull? What abbreviation do you want to give force? Cool, I'm good with that. And then we're going to name the SI units after the developer of those laws. And so the SI unit is the Newton. Now, 1 Newton is conveniently 1 kilogram. That is accelerating at 1 meter per second squared. So a Newton is a kilogram meter per second squared. Not just is it a kilogram is a meter per second squared, but there's no, I always hear kids say kilogram per meter per second squared. That's not a slash. There's not a dividing line right there. It's kilogram meter. Okay? They're right next to each other. They're both in the numerator. Kilogram meter per second squared. And we could always use kilogram meter per second squared because Newton's just a composite unit of the kilogram meter per second squared. But how often do you want to say kilogram meter per second squared? Do you want to say we multiply our kilograms and we multiply it by meters per second squared, and then we have a kilogram meter per second squared, and so every time we have a push or a pull, we're saying kilogram meter per second squared, so we've got 15 kilograms meters per second squared minus 5 kilograms meters per second squared. What's easier? Why don't we just substitute in another word, right? So we say Newton. Newton's way easier. Forces can be blank or acting at a distance, at a range. This would be contact. That's, how close is that? That's so close it's touching. And so acting at a distance would be a field force. Okay? There's 4 basic types of forces. We've got an attractive force that exists between all objects with mass. What are massful objects that are attracted? They have gravity. So gravitational force. That would be the correct part of speech. We're looking for an adjective. Attractive or repulsive forces between charged particles. Oh, I heard electric. I heard magnetic. Electromagnetic, good. So there's like 3 parts of that. There's electricity, there's magnetism, and then there's the weird combination of the both of them. Because they're kind of the same force, but kind of not. They interact in different ways. And then blank forces is in radioactive decay of small nuclei. Nuclear. And then an attractive force between particles in the nuclear. Yes! These are the strongest of the 4 forces. We're going to have to describe these. This one's probably strong nuclear. So then the other one's probably... Oh. Good. We know our forces. We've got our forces labeled. So Newton's first law says an object in motion... Right. Remains in motion. The reason why I switched to remains in motion is because stay has a connotation to it of not non-motion to non-English speakers, or like not trying to equate the two, but like when we're giving commands or things like that, stay would be like a dog's command to stay put. In this case, we want to stay in motion, which means to keep moving. So I just use the word remains to not confuse people. Is that weird? I think it makes more sense. Mm-hmm. Yeah. So then, if it remains in motion at a constant speed and moving in a straight line, then an object at rest, you could say stays. This is also called the law of inertia. All right. So the law of inertia. Yeah, if you just hand that to me ASAP, that'd be great. Yeah. Yeah, sorry. They ratted you out, sorry. Inertia. This comes from a deeper conversation that inertia is a measurement of mass, and you've had this in chemistry where when you were measuring things, what's the verb that we should associate with the way you measured things and the quantity of a substance and how much substance you had? We would probably put it on a scale and we would find its mass. So if we put it on a scale and we find its mass, what was the verb associated with that? You would mass it. So ironically, we still use the word weigh to it, right? We weigh it. And the reason why we weigh to find mass is because we actually have to calculate the mass from the fact that we're on planet Earth and that mass gets pulled down, right? But if we were on a different planet, an electronic scale, like we bring it to the moon, probably wouldn't say that it weighs as much, right? It would probably be, but is it the same amount of material though? So it has the same mass, and that's the inertial value, is how much particles it's made up of. If it has the same number of protons, same number of electrons, made up of the same amount of stuff, that is mass. But now our scale wouldn't read correctly because it's weighing, it's getting pulled down less on the moon, right? And so on the moon, it gets pulled down less, it weighs less to have the same mass. And that's why your chemistry teachers were pretty particular in talking about its mass, because they're worried about how many protons and electrons it's made up of. As far as this class goes, though, this is where we start to weigh things to find the force. And when we say weight, that literally is the force due to gravity, right? Not the acceleration due to gravity anymore, but we're going to take that acceleration, A, and multiply it times mass, F equals ma, to get the force or the weight in newtons. Inertia is the fact that things don't move. So not only would, I'm thinking of one of my first year teacher moments. I had this kid who ended up playing for U of H the next year as an O-line, or I think it was like a center. Pretty big guy, Jacob Abels. And did he weigh a lot? Yes. But he was also massive. And he could move that mass, which means he produced a lot of force, right? And when I say massive, that means somebody else trying to push him would need a lot of force. He is massive. It's harder for him to be moved. Okay? Does that kind of make sense? He's massive. He's harder to move. Guys, if he's massive, even in outer space, you could get him moving, but the equal and opposite interaction, man, you push him, and it's almost as if he's pushing you. Okay? All right. Equilibrium. An object is in equilibrium with the velocity is 0 or its velocity is constant. You don't need a force to keep a body moving at a constant velocity. All right. So equilibrium is when all the forces equal 0. So there's no acceleration. Inertia is a measure of how an object blank changes in motion. Why am I blanking on this blank? Let me pull out my other notes. Where are my other notes? I was doing pretty good without having any notes out. Okay. Inertia is a measure of how an object resists change in motion. It's a measure of an object's mass. I wanted to put mass in there. I think that's what my brain was doing. Inertia is a measure of how an object resists change of motion. Can an object be in equilibrium if only one force acts on it? No. Why not? Right. So if you have one force, it implies that you have a non-zero interaction. You need something else to bring it back to zero if you have something that's non-zero. It's like, if I have 5, do I have 0? But if I have 5 plus x, could I get to 0? Probably, yeah. All right. I'm not going to write that down. I have a long blurb on my previous one, and it pretty much said, if I have a non-zero force, if that one force is non-zero, then another force is needed to balance that out. I don't know, something like that. All right. Newton's third law. Let's talk about Newton's third law. Every force has an equal and opposite force. So the action is object A exerts a force on object B. The reaction then is object B exerts a force in the opposite direction. On object A. Even without this parentheses, what is the difference between the two phrases in action and reaction? English people. So y'all are like, oh, it's a call and response. No, what I'm trying to, not no. I mean, here's what I'm trying to get at. What changed grammatically about part action and reaction? What changed in these two statements? That's what I'm really asking. The what and the what switch places. The object and the subject. So this in English class, it'd be the object and the subject switch places, right? I just flip-flop the subject and the object. All right. Now keep that in mind. I have this question for you. Consider this apple on this table at rest. If we call the gravitational force exerted on the apple action, what is the reaction force according to Newton's third law?